Welcome to my channel and thanks for keeping time with me. Today we are going to learn about a post-hoc test associated with analysis of variance. But before I go into SPSS for the demonstration, let me quickly give you a brief synopsis. When you perform a one-way analysis of variance, the output of the ANOVA shows if there is significant difference among the means of the groups or treatment without indicating where the differences lie or which mean is significantly different from another. If you have a project or experimental design that requires you to identify where the significant difference among the means lie in order to make judgment or reach a conclusion, then it becomes imperative that you must carry out comparison of the means in a process called post-hoc test of multiple comparison. The post-hoc test you can carry out includes any of the following. 1. Tokyo. 2. Duncan Multiple Range Test. 3. Least square difference. 4. Beffaroni. 5. CDOC. And 6. Dunet, among others. These post-hoc tests are some of the different methods of comparing different statistical means or averages within an experimental design that requires analysis of variance. The list here is not exhaustive. You are hereby advised to choose any one of the post-hoc tests that is suitable for your experimental design or project, putting into consideration the risk of committing type 1 and or type 2 errors. However, in my previous video on ANOVA, I discussed in details Tokyo post-hoc test of multiple comparison. If you are interested, you can see the video on my YouTube channel by clicking on the link given in the description section. But in this video, I'll be performing the Duncan Multiple Range Test in SPSS and demonstrate how to interpret the output and use the compact letter display. My name is Titocan and this is Titocan Solutions, a YouTube channel for improving the knowledge of how to do things. Duncan Multiple Range Test is one of the post-hoc tests of multiple comparisons that determine specific significant differences between pairs of means in the output of analysis of variance. It belongs to the general class of multiple comparison procedures that use studentized range statistics Q to compare sets of means, and its application has the following advantages. 1. The Duncan Multiple Range Test is preferably suitable for datasets with large number of groups or treatments having larger pairs of means to compare. 2. The use of Duncan Multiple Range Test lowers the risk of committing type 1 error. So using Duncan Multiple Range Test helps to avoid the incorrect rejection of the null hypothesis. 3. The output of the Duncan Multiple Range Test is provided as a homogeneous subset table, that is, a table that shows which groups have the same mean and are not significantly different, and which ones have different mean and are significantly different. Please kindly put this knowledge into consideration because we will be dealing with it during the demonstration in SPSS. And 4, compact letter display is a necessary adoption from the homogeneous subset and used as an imposed superscript to each mean value for easy identification of significant differences or similarities. Compact letter display facilitates the easy identification of variables, groups, or factors that have significantly different means or averages and the ones that do not have significantly different means or averages. The technical application of the compact letter display is to use one or more letters of the alphabet to label the variables or group means at the superscript position for ease of identification of significant differences or similarities. The application of the compact letter display is technical and may be confusing, but in this video, I will show you how you can be able to do it easily and present your results in a table with the compact letter display. Now, let's go into SPSS for the demonstrations. First, let's take a look at the dataset for this demonstration. This is the dataset already loaded into SPSS. This data is fictitious and is created and organized to suit the demonstrations in this video. To learn how to load data into SPSS, kindly see my video on Introduction to SPSS Software for Beginners, Part 1. This table of data contains 10 groups of spatiotemporal information of water temperature, water depth, and water clarity, sampled monthly at 10 different stations within a river channel. This data has been collected and restructured to meet the condition for a one-way analysis of variance. You must ensure that your data is tenable for analysis of variance. Please see my video on analysis of variance in SPSS, effect size and interpretation to learn more about ANOVA and the assumptions that must be satisfied. The link to the video is given in the description section below. Now let's get started. Go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Compare Means. And from the drop-down options, click on One-Way ANOVA. Immediately, the One-Way ANOVA dialog box opens. Now hold down the Control key on your keyboard and from the box on the left, select your dependent variables. That is the water temperature, the water depth, and the water clarity. And then click on this transfer arrow key to move them to the dependent list box on the right. Thereafter, select the independent variable, which in this case is the station. These stations consist of 10 groups. Now, click this transfer arrow key to move it to the factor box. At this point, we have set the SPSS system to perform the analysis of variance. But since we are interested in performing the Duncan Multiple Range Test as the multiple comparison of the mean values produced by the ANOVA, we will take 2 more steps further. Now, click the postdoc button and this opens the one-way ANOVA postdoc multiple comparisons dialog box. This is where you can select any of the postdoc tests of multiple comparison you might wish to carry out. But for this video, I am only interested in the Duncan Multiple Range Test. So under the Equal Variances Assumed section, I will select the box for Duncan to select the Duncan Multiple Range Test. This selection takes into account the mean values calculated under ANOVA and compares them accordingly and provides the output as a group of homogeneous subsets in table columns, with p-values attached to each subset at the bottom. On this dialog box, ensure that the significance level is set at 0.05. This is necessary because 0.05 or simply 5% is a conventional alpha value that provides a strong assumption of the null hypothesis. However, you can reduce or lower it to 0.01 to raise the standard, but for this Duncan Multiple Range Test, I will leave the significance level at 0.05. Then click Continue to close this dialog box. Now, click the Options button to open the One-Way ANOVA Options dialog box. In this dialog box, check the box for Descriptive. This selection produces the descriptive statistics, which includes the mean values that the Duncan Multiple Range Test will assess by multiple comparisons in the postdoc test. Then click Continue to close this dialog box. For the purpose of this video, there is no further selection to make. At this point, we have selected every requirement to perform the Duncan Multiple Range Test. Now, click the OK button to produce the results in the output window. The results have been produced and the output includes the descriptive statistics table, the ANOVA table, and the postdoc test homogeneous subset table, which presents results of the Duncan Multiple Range Test for each variable. As you can see, this is the table for water temperature, this is the table for water depth, and this is the table for water clarity. But before I concentrate to interpret these Duncan Multiple Range Test results, it's important that we look at the descriptive statistics table and the ANOVA table respectively. Now let's scroll up to the descriptive statistics table. In this table, double-click anywhere to pivot the table. Here in this table, the variables, that is water temperature, water depth, and water clarity sampled at their respective stations are given in column 1. The stations are given in column 2. The number of groups or treatment are given in column 3. And as you can see, there are 10 special groups. The mean, the standard deviation, and the standard errors are also given in this table, including the 95% confidence interval for computing the mean values. Their dispersions, that is, the minimal and maximal values, are also given in this table. As important as every information in this table is, but in this demonstration, I am only interested in the variables, the stations, and the mean values. So I extracted them as appropriate from this table and moved them to the Word document, which I reorganized as appropriate without altering the original information, as you can see. Here in this table, column 1 is the stations, column 2 is the water temperature, column 3 is the water depth, and column 4 is the water clarity. Like this, we have made the table ready for Duncan Multiple Range Test assessments. However, as you can see in this table, it is glaring that the mean values of each variable at the different stations are nearly the same. So it can be tempting to quickly conclude that there is no significant difference among the variables. But for a reliable conclusion, you are strongly advised to check the results of the analysis of variance to confirm whether there is significant difference or not, or whether to reject the null hypothesis or not. Now let's return to the SPSS output window and scroll down to the ANOVA table. In this ANOVA table, the most important column is the p-value, designated in this table as xig, meaning significance value. From this ANOVA table, if the p-value is greater than 0.05, it means there is no statistical significant difference among the means of the variable. But if the p-value is less than 0.05, it means there is statistical significant difference among the means of the variable. As you can see, the p-value of the water temperature is 0.499, which by comparison is greater than 0.05, indicating that there is no statistical significant difference in water temperature among the stations. But the p-value for water depth and water clarity is 0.000 each, and by comparison, 0.000 is less than 0.05. This indicates that there is statistically significant difference in water depth and water clarity respectively among the stations. Now, since there is significant difference in water depth and water clarity, the question now is, where exactly is the difference coming? Where among the stations is the variable different? In which station is the mean value significantly different or the same? These questions are what ANOVA does not usually provide an answer for, hence the need for the Duncan Multiple Range Test to help identify where the specific differences lie. Now, let's scroll down to the post-hoc test section to view the homogeneous subset table of the Duncan Multiple Range Test results. This session is the main objective of this video, and I hope you see this video to the end because there is more to learn. The simple rule of thumb for Duncan Multiple Range Test is that within a subset, the p-value at the bottom of the subset is usually greater than 0.05, indicating there is no significant difference among the means in that subset. While between the subsets, there is a significant difference. But between subsets or columns where a mean value is repeated, there is neither a significant difference in the first subset nor a significant difference in the subset where the mean value is repeated. Now, let's apply this rule of thumb to the homogeneous subset table of Duncan. Table 1 is water temperature. As you can see in this table, there is only one subset, and that's because in the ANOVA table, the p-value for water temperature is 0.499 and greater than 0.05, indicating that there is no significant difference. Hence, the presence of only one subset here in this table. On the other hand, according to the rule of thumb, the p-value of the subset is 0.110, and by comparison is greater than 0.05, indicating that there is no significant difference. So the water temperature is not significantly different among the stations. This implies that the water temperature is statistically the same in all the stations of the study area. To apply compact letter display, let's move this table of water temperature to Excel spreadsheet. To do this, right-click anywhere on this table and then click Copy. Then open the Excel spreadsheet and paste using Ctrl+V on your keyboard. In this table, there is only one subset. Now, change the number 1 on top of the subset to letter A. And since there is no significant difference, the mean value at each station will be replaced by a small letter a, indicating that the water temperature is statistically the same at all the stations. Then go to the mean table in the Word file and insert this letter A alphabet next to the mean value as you can see. Then highlight the first letter, hold down the Ctrl key on your keyboard and highlight the remaining letters. Then go to the toolbar and click on the S square to make them become superscript to the mean values of water temperature. This is how to apply the compact letter display, and as you can see, this one is straightforward. Now let's return to SPSS output window and proceed to the homogeneous subset table for water depth. Table 2 is water depth. As you can see in this table, there are two subsets here. That is subset 1 and subset 2. According to the rule of thumb, the mean values in subset 1 are not statistically significantly different among the stations because the p-value of the subset is greater than 0.05. And similarly, the mean value in subset 2 are not statistically significantly different among the stations because the p-value of the subset 2 is greater than 0.05. This indicates that the water depth at station 9, station 3, station 8, station 5, and at station 10 are not significantly different. Similarly, the water depth at station 4, station 2, station 1, station 6, and at station 7 are also not significantly different. But the water depth of the group of stations in subset 1 is significantly different from the water depth of the group of stations in subset 2, since there are no repeated values between the two stations. Now, to apply the compact letter display, let's copy this table and paste it in Excel as usual. Now, replace the number 1 and the number 2 at the top of the subset to letter A and B respectively. Then, change all the mean values in subset 1 to letter A. And change all the mean values in subset 2 to letter B. Then, bring out the common letters and place them in a different column outside the table like this. So we now have A, 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 and B, 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 and B as the compact letter display. Now go to the mean table in the Word file and insert this letter A and B alphabet as superscript to the mean values of water depth as appropriate to their station numbers. That is, station 9 is A, station 3 is A, station 8 is A, station 5 is A, and station 10 is A. Similarly, station 4 is B, station 2 is B, station 1 is B, station 6 is B, and station 7 is B. Now, highlight one of the letters, hold down the Ctrl key on your keyboard, and highlight all other letters. Then go to the toolbar and click on S square to raise the letters as superscript. Like this, we have applied the compact letter display method, and it makes the table glaring to see the stations where the water depth is similar and where it is different. Now again, let's return to the SPSS output window and proceed to the homogeneous subset table for water clarity. Table 3 is water clarity. This table is different from the previous tables, and the approach here will be different. As you can see in this table, there are 3 different subsets. That is subset 1, subset 2, and subset 3. According to the rule of thumbs, there is no significant difference in subset 1, no significant difference in subset 2, and similarly, there is no significant difference in subset 3 because the p-value at the bottom of their subsets is greater than 0.05 respectively. But between subset 1 and subset 2, there are repeated mean values at station 5, station 6, station 3, station 1, and station 9, which makes subset 1 and subset 2 similar at those stations. So there is no significant difference, and generally, the water clarity is therefore similar at station 4, station 5, station 6, station 3, station 1, and at station 9, as you can see. Furthermore, we can specifically say that the subset 1 has mean values that are significantly different from the subset 3 because there are no repeated mean values between the two subsets. Similarly, we can specifically say that the subset 2 has one mean value that is significantly different from the subset 1 and subset 3 respectively, because there are no repeated mean values between them. So as you can see, the water clarity in station 4 is significantly different from the water clarity in station 7, and the water clarity in station 4, station 5, station 6, station 3, station 1, and station 9 are significantly different from the water clarity in station 10, station 2, and station 8 respectively. Water clarity in station 7 is significantly different from the water clarity in station 4, station 5, station 6, station 3, station 1, and station 9, as well as significantly different from the water clarity in station 10, station 2, and station 8. Now, there is something peculiar about subset 1 and subset 2. As much as station 4 in subset 1 is significantly different from station 7 in subset 2, they are not significantly different from station 5, station 6, station 3, station 1, and station 9 respectively because of the repeated mean values. Occurrence like this makes the use of compact letter display important in expressing the Duncan multiple range tests. Now, let's apply the compact letter display to water clarity. As usual, let's copy this table and paste in Excel. Now, replace number 1, number 2, and number 3 at the top of the subset to letter A, B, and C respectively. Then, change all the mean values in subset 1 to letter A. Then change all the mean values in subset 2 to letter B. And then change all the mean values in subset 3 to letter C. Now, let's bring out the common letters and place them in a different column outside the table for compact letter display. That is, station 4 is A, station 7 is B, and station 10, station 2, and station A as C each, because these stations do not have repeated mean values in their subset. Now, since station 5, station 6, station 3, station 1, and station 9 have mean values repeated in subset 1 and in subset 2, then their common letters will be AB for each station. So for compact letter display, we now have A, AB, 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 B, C, C, and C. Now let's go to the mean table in the Word file and insert this letter A, B, and C alphabet as superscript to the mean values of water clarity as appropriate to their station numbers. That is, station 4 is A, station 5 is AB, station 6 is AB, station 3 is AB, station 1 is AB, and station 9 is AB. Station 7 is B. Furthermore, station 10 is C, station 2 is C, and station 8 is C. As usual, highlight one of the letters, hold down the Control key on your keyboard, and highlight all other letters. Then go to the toolbar and click on the S square to raise the letters as superscript. Like this, we have applied the compact letter display method to water clarity. Now, generally looking at this mean table with the compact letter display, it becomes glaring to identify quickly and easily stations where variables are not significantly different and stations where variables are significantly different. Here in this table, the water temperature is the same in all the stations. The variable water depth is only the same at the stations with the same superscript letter and different otherwise. For example, water depth at station 1, station 2, station 4, station 6, and station 7 with superscript letter B are either deeper or shallower than the other stations with superscript letter A. Similarly, the water clarity at station 4 is not the same clarity as station 7, and similarly, not the same clarity at station 2, station 8, and station 10. However, the water clarity at station 1, station 3, station 5, and at station 6 are not different from the water clarity at station 4 and at station 7 respectively. Now you are done with your analysis, and from here, you can begin to find scientific justifications to why there are similarities or differences of the variables in your study area. This is how to perform Duncan Multiple Range Test in SPSS and interpret with compact letter display. I hope this video was useful to you, because right now we have come to the end of this video. I hope you will be able to replicate the procedures as demonstrated in this video to perform Duncan Multiple Range Test of your own data in SPSS and interpret it with compact letter display. If you like this video and you want to see more video contents like this, please give this video a thumbs up and please subscribe to my YouTube channel to encourage education and learning, and so that you receive notifications every time I publish new and useful content. Subscription is free. Thanks for your time and subscription, and I hope to see you again in my next video. Bye.